Thanks, Gerald, and thanks, Chip.
Yeah, and I just sent you the file.
Okay, cool. I'll post it in about 3 minutes. Welcome to the Propeller 2 live forum. It's December 29th, 2 p.m. And today we have a topic from Chip. Before we get him going, there are no community announcements this week. We've just been too busy with too many other fun things. Tomorrow also, if you'd like to join us for part 2 of Johnny Mac's presentation, it was a lot of fun last week. For those that didn't attend or did not watch the video, John really took us into how these RGB LEDs work, and then how he built the object, and then how to use the object. And you may have seen all kinds of fun things that were posted on the forum through the last week as a result of him showing us the way with this. So I felt like we have the best, most functional LED object available. So thanks, John. And tomorrow we're adding the encoder to this project too. And I think some of the code's already been posted. That's at 4 p.m. Pacific. Sorry, it can't be earlier, but we just picked that time because the P2 Live Forum was initially before it until we moved the last couple of weeks till Tuesday. So Chip, here's your agenda. You're free to go. You don't have to follow this.
Yeah, it's actually changed a little since then.
Yeah, that's fine. And so I'll go get your code now and I'll post it on Google Drive, and then I'll put a link so everyone can download it.
All right. I'll share my screen here so that, oh wait, after you can.
I'm all done.
Okay.
So just give me about 5 minutes to get the zip file together.
All right. Let's
see. By
see.
the way, Chip, while you set up, we have some new guests here today, which is pretty exciting. I know we have at least one from Argentina, and yeah, I see a few names I don't recognize, and we have probably the youngest person involved now, whose name is Kevin. He was here last Wednesday, and thanks to a little help from David Betts, he will soon be the recipient of a Johnny Mac holiday kit and a P2 bundle with an edge.
Right.
Yeah. I mean, imagine when you were 10, if you could have had that kind of technology in your hands.
Oh yeah.
I mean, you wanted a manual milling machine at that age, and this kid gets a P2.
Right. Well, and a jetpack would have been good.
Yeah.
Or a dirt bike maybe.
So his hardware arrives tomorrow, so maybe he'll be able to get it put together in time for John's presentation.
Okay, great.
That's very cool.
Yeah, and it also was suggested by a couple forum members that we find a way to recirculate funds and hardware back to these students, that because there are many like him, but we haven't quite figured out how to do that yet in an easy way, but I'm sure it'll happen.
I don't want to really brag about it, but as those first ever boards came out, I talked to Eric, and he said he hasn't just doesn't have the funds to buy one, and I sent him one. So I basically gave Eric the first P2 board.
Super. Can everyone see this drawing?
Yep. Yep.
Okay, so this is the DAC that exists in each pin. And it's a really simple circuit. You can see it's kind of like a thermometer code thing where, and this is a little bit of a simplification. The way it's implemented is we have 16 groups of what are equivalent to 16 resistors, and then we have, let's see, an 8, 4, 2, and 1 resistor. But in concept, it works like this. You see that there's this M7 through 0, right, up there. And these are values that, this is the 8-bit DAC value. So this DAC is 8 bits, and it has about 10.5 bits linearity. But by giving it an 8-bit code, you cause some of these resistors to be pulled low and some to be pulled high. And so if this thing is given the value 0, all of those double inverters are outputting lows, and that sums on the DAC output to 0 volts. if you give this thing 255 or FF hex, it's going to turn all those resistors high. And I've just shown the first and last three to keep it simple. But so what you have here is a constant impedance DAC, which is really important for pushing high frequency signals. You can't have like it's simpler maybe to make like an R2R DAC, but the trouble is it's going to be very high impedance. So if you want to drive really fast analog loads like video, there's no time for any kind of feedback loop like in an op amp or anything. You have to have something just really, really simple like what this is.
Okay.
And the implication here is that you can see like what happens if you output the value 80 hex. What do the resistors look like?
Well, the very last resistor will be set and all the others will be cleared.
With 80 hex, half of them will be on, and half of them will be low, and half of them will be high.
No,
Right?
wouldn't that be 7F?
7F or 80, same thing almost. Yeah, see, you're thinking like R2R, I think. This is like a total brute force approach to a DAC where you actually have 255 resistors being driven by inverters. And the impedance is all controlled so that everything is considered like the impedance of that double inverter is considered with the resistor. So everything's super accurate. So if you give this thing a midpoint value like 7F or 8.0, then 127 resistors are going to pull low and 128 are going to pull high, or vice versa. So
it's not to do with what bits are set in the pattern.
It's the magnitude of the value.
I see.
Yeah, because see the bottom one, it says if it's greater than 0, then that's a 1. If the next one is great, if the M7 through 0 is greater than 1, then turn on the second inverter, make it high. If the on the third inverter, if the value is greater than 2, then make it high. So this is going to operate just like a thermometer, right? It's going to go up and down. And so at the extrema, you don't have any DC current flowing, but at the midpoint, you have half the resistors pulling high, half pulling low. So you have a fight going on, which dissipates power, but the impedance is constant, which is an important thing for high speed like RF and video signals. So this is about as simple as a DAC as you can make, but it's good for what we want because it's universal. It kind of does everything. And we actually have 2 of these DACs in each pad. One is built from 252K resistors. That's the 990 ohm DAC. And then the other one is built from 31.6K ohm resistors. And this results in a net impedance of 990 ohms for the big one, or 124 ohms for the lower impedance one. And then we have this other little resistor down here called RP. I just said P for pull down. So RP has a value of for when it's in 124 ohm mode, RP has a value of 190 ohms. So when that switch gets pulled low, the DAC, if you look at the bottom table entry, the DAC goes to 75 ohm output, which is super low, with a 2.0 volt peak. And 2.0 is significant because in the case of video, when you drive this DAC out into another 75 ohm load to ground, it just becomes 1.0 volt peak. So you have video signals there. And this DAC, the way we built it in the chip is there are flip-flops that actually drive all of these inputs to these inverters. And these flip-flops all register at the same instance. So all of the thermometer decoding is done in logic before the flip-flop. So that when the flip-flop updates, all parallel outputs change at once. And within about 2.5 nanoseconds, this thing settles down to within an LSB. It's super fast. And there are 4 different modes here. There are 2 3.3 volt modes, which are 990 ohm and 124 ohm. And then if you enable this pull down resistor, you get either a 600 ohm DAC at 2 volts or a 75 ohm DAC at 2 volts. So if you're driving like maybe audio that doesn't need to be super high fidelity, you can save just by using the first DAC mode, which is 990 ohms. But if you have some fast loads or that you want to really control with a real stout drive, then you want to select the lower impedance DAC, which is it's gonna burn more power, but it's gonna be a lot less flimsy. Okay, so any questions on this DAC? All right, I'll go into
Chip, quick question. Can we do 12 bits on the DAC and also 12-bit A to D?
yes, and I'll get into that.
All
These
right.
DACs you see are only 8-bit, right? So they're pretty limited. However, we have smart pin modes which can dither the DAC between 2 adjacent values. Like if you want to output, let's say we have a 16-bit mode, right? So if you want to output 80 hex, well, that's actually between 0 and 1 on the 8-bit DAC. So what it would do is spend half the time outputting 0 and then half the time outputting 1, which would be realized just by this bottom inverter toggling at 50% duty cycle. And that would actually create a half step between value 0 and value 1. And so we have the smart pin stuff can actually take any value and dither, it takes a 16-bit value. The top 8 bits drives the DAC directly, and the bottom 8 bits is added to in some fashion, either with random noise or with a counter, so that we get a PWM out, and then that causes the DAC to transition to the next value up periodically. And I have a little demonstration of how that works today.
And your zip code never made it over to me. Make sure you
Okay.
hit send.
Let's see, I think I did. Oh, wait. No, there were errors attached to your file. Oh, you know what, Ken? Because there's a, okay.
You're sending viruses
Because
around.
there's a zip, it's a zip with an EEX, it didn't like it. So I'll get it to you in just a little bit. Should I do it right now? It's gonna take a minute.
Yeah, or you can upload it directly to Drive.
Oh, okay, let me just do that.
Yeah.
Hold on, everybody, this will take just a sec. Let's see, Drive.
And the settings won't be totally clear on how to make it fully publicly shareable.
Oh, what I'll do is I'll just put it on Drive right now, and I'll give everybody
Okay.
a link to it. All right, let's see.
You'll need to, since you're going in with your Parallax account, click on it, and where it says share with Parallax, just change that to share with everybody who has a link.
Right, okay.
Okay.
Hold on. Let me go. I got to get out of the car and back into the car. Right, okay.
So for those that have joined on, I kind of routinely go through and mute people when there's a lot of background noise, but please don't take any offense. You can talk anytime you want, but I'll just keep track of your microphone for you if you're making too much background noise.
All right, almost there.
Or type your question out like Roy said.
I apologize for that, Ken. The wind's blowing like 80 miles an hour here through my window, and it's probably picking it up and sounding like somebody's blowing this place up.
No worries. Maybe you should enable the camera outside so we could see the storm.
No storm. It's just the typical Santa Anas in Southern California.
All right. Okay, what I'll do is I'll just paste the link right into the chat, okay?
Yeah.
That way everybody can get it. Let's see. Where is the chat?
And Brian, you could ask your question too.
Greg, that's just our Southern California weather. We got rain yesterday and wind today. That's winter.
Yeah, absolutely. Absolutely. We got like so much rain yesterday. All my drains in my backyard are plugged up. So my backyard was under like 4 inches of water.
Fun times.
All right, so I posted that thing to the chat. So let me pull up. Let's see here. All right.
And we assume that's downloadable by everybody.
Should be. Yeah, I sent it to everyone. All right.
And also, Chip, before you go too far, I had the dummy question, remember? Show me where you use DACs. I mean, I realize I use them and don't think about it because they're always in other objects or projects people have done.
Right.
Are you going to cover that too at some point, right?
Yeah, so, okay, so I'll just go over DACs really quick. DACs are digital to analog converters. So they take a number and they turn that into some kind of analog voltage or current. In our case, we have voltage, but you could kind of use it in current to a degree too. And then ADCs, or analog to digital converters, they go the other way. They take an analog current or voltage and convert it back to a number. So once you have things in numerical form in the processor, you can run all kinds of equations on them, and then you can re-output them to DACs. That's called signal processing. Okay, so DACs, they get used for video, for audio, for all kinds of control signals. People on the forum would probably say more than me about it, but they're useful. Okay, can you see this little screen here?
Yep.
Okay, so this is just a way to use the DAC. Oh, let me open up one other file. I made a new thing that I put into the main silicon document. So in the smart pins, there are ADCs and DAC modes. So if you go down here to the second up from the bottom, these are the DAC modes. And these are binary patterns, and these are written into the pins via the write pin command. So if you see these DAC 990 ohm, and then at the bottom is DAC 75 ohm, you see those binary codes to the left, those enable these various modes. And so to turn a pin into a DAC, all you do is you write that code into the mode register, and then in that DD field, you put your 8-bit value. This is the simplest way to use a DAC. Like I said, the smart pin can toggle those D values between two adjacents to give you like a 16-bit resolution. And the streamer can just spew data out to those values over what are called DAC channels. And I'll show that in a little bit too. But basically, this is the mechanism. You just write this to the pin, you put your 8-bit value where it says DD and so on, and then you make the pin, you set the DIR bit high, so the pin turns on, and then you have a DAC. So I have here, this is something that's just kind of a symbol that we have that selects one of those modes. It selects the full span 124 ohm mode, which is the stout full range 3.3 volt DAC. And what it's going to do here, it's going to make the pin an output, right, which will cause it to go low because it's in digital mode. And then in a loop, excuse me, it's going to write that configuration value to that pin mode register along with this in the that 8-bit field, and it has to wind it up another 8 bits in order to get it to fit, because those 13 mode bits that I showed in that chart are actually lifted up by 8 bits when you do the write pin. So in very simple form, this is all you need to do to write a DAC. You just set the mode, give it the value, and then make sure it's an output, and you'll have an 8-bit DAC. And from last week, remember we had that oscilloscope thing working? I turned it into an object here so that now we can start it up. We can say what pins we want it to watch, and then what kind of rate we want it to sample at. Whereas 8 with all zeros after it would be 100%, 4 with all zeros would be 50%, but you can make any kind of integer value. They don't have to be powers of 2. So what I've done here, I don't know if you can still see my little camera view, but I've jumpered pins 8 through 11 down to pins 0 through 3. So for these demonstrations, pins 0 through 3 is going to be acting as a debug scope using the scope mode of the pins, which are little filtered ADCs. And then it's going to be driving analog outputs from pins 8 through 11. So in this case, we just have pin 8. So, and rather than like, I could point the camera at my scope, but we're going to use the debug scope here. So simple scope is going to get pulled in here, and we're going to start it right here, and then it's going to monitor what we're outputting on this pin. So when I run this with the control F10, let's see, why does it expect? Oh, because I added something. What did I add to it? Oh, I added the mode that we need. ADC1X. I think that's what we need here. I forgot. I made it so I could actually set the modes up so that we can give it magnification mode. So when I run this now, we can see that we have a little ramp signal. And that's because this I++ here is incrementing, and then we're limiting it to 8 bits, and we're inserting it into that bit pattern, and then we're writing it to the pin. Any questions on this?
Chip, I just want to say that's cool. But also I want people to know that you're using Peanut, and these features are not, the graphing features are not yet in Prop Tool, just
Right.
so that's clear. But I do have a question. Can you go over, I understood the starting value, but then this, you increment it I++, and then you have this hex FF. Is that then 100% and you're just going there one step at a time?
Yeah, it's going from 0, 0 to FF. So I is a 32-bit integer that just keeps incrementing, but we're just taking the lower 8 bits of it. And we're melding that into that control pattern to set the DAC mode up. And then we have to shift it left by 8 because of the way there's 32 bits in this, you know, data that goes to the mode register in the pin. And it so happens that the low-level pin stuff is shifted up by 8 bits from the bottom. So that way the lowest 8 bits in that whole 32-bit frame are where the smart pin modes are. So if you don't want to do any analog stuff, you only need to write values which fit into 8 bits, which become like simple, you know, non-augmented 9-bit values in assembly language. So the modal bits for the highest level modes are in the LSBs of this thing, so that you don't need to always have big values. But when you want to write a DAC value, you have to configure this thing, and it means doing more than 8 bits. And that's what these patterns are. In fact, this I could pull up. Let's see. Let me see here. I'll just move a window.
And Chip, what's the ramp frequency?
Oh, okay. So yeah, everything is kind of virtualized here. So we're sampling it at kind of a low rate here. I think it's about 200 microseconds. So it's in 200 microseconds, it's doing 256 of these steps. So it's about 1 microsecond per repeat loop.
And that's really driven by the fact you're graphing it, right? Because you don't have any pauses in here.
Yeah, I don't have any like timing reticule or graticules on this scope display. So
okay.
It's 512 samples, and this is all being pulled in from that thing called Simple Scope.
And for those hooking this up right now to run on their own, can you go over the pins that are on the DAC and the ADC? Again, which pins are jumpered to which?
So, okay, one thing, remember to add this comma P_ADC_1X, because I forgot, I've been changing things and I added that later. I didn't go back to this first file. So you have to put this in, and I'll update the zip soon to have this. But so what I'm doing is the scope, I'll just load Simple Scope here. Just take a quick look at it. It's an object which it's just this, it has some assembly language in it. It sets up a scope display. When you call it, you give it the pins rate in the ADC mode, and then it launches a new cog with this method, which has the assembly language. Oh, there's the whole thing right there. It sets up a scope display, you know, with 4 channels, and then it starts the ADC pins on, I'm usually giving it 0. So I have everything jumpered from 8 to 11 down to 0 to 3 on my board. So I'm outputting on 8 to 11 and then inputting on 0 to 3. And this object is catching it and showing the data via the scope display. So these are just some things it sets up for the assembly program, so we don't have to do a bunch of math in assembly. And then here it just does the job where it waits for a trigger. It also, I added a timeout. This didn't exist last time. For any wait instruction, if you do a set queue beforehand, it allows you an opportunity to set a timeout rather than wait indefinitely. So I get the count, I add the timeout, which is going to be seconds divided by 20. It's going to be 50 milliseconds. So it sets a 50 millisecond timeout. So in case no trigger event comes, it's like a scope on auto trigger. It just will show you the data anyway, so that you don't wonder what's happening. And here it waits for the trigger, or it times out. And here it then takes a snapshot of the incoming stream. And then it waits for it to end, and then it sends it off to the debug display. Does that answer, Ken? I know it's maybe a lot of information, but.
Yeah, you just give it the starting pin, right? Then back in your spin code.
Whoops. Well, hold on here. So if we go back to this first file here, yeah, right here where I started up, I say I only want it to show one pin, so it can actually watch 4 pins, but I just wanted it to show 1 pin. So when we run this, you know, we see this waveform. And see the bottom 3 are just kind of laying on the bottom. That's channels 1, 2, and 3. It didn't enable those. It's the scope is capturing and displaying them, but those aren't actually enabled as ADC inputs. So they're just reading low.
Yeah, that explains it. I just want some comments on those parameters so I could know what they are.
Yeah, gotcha. All right, now here is the same thing, okay? We're setting the scope up the same way for 1 channel, same frequency, but here we're gonna do it in assembly language. So I do an org, this is some inline assembly here. So we make the pin an output, whoops. And then in a repeat loop, to just be really quick, I just repeat these 3 instructions, and each of these takes 2 clocks. So this is taking 6 clocks, right? So in 6 clocks, in first 2 clocks, it increments level, and then it moves that byte into this bit field right here, right? Of this big modal value. See, this is that thing we were looking at before, that symbol. Here's what it equals. So it's this bit field right in the middle that we care about. So we're going to increment I and then cast the lower 8 bits right into this, which was put on a byte boundary by design so that you can do this kind of thing. So we write 8 bits into it, and then we we increment the level, move the level into mode, and then we do a write pin. And at the point we do the write pin, the pin is, you know, still in DAC mode like it has been, but it has new bits, you know, in the data field for the DAC. So this thing's going to run a lot faster. In 6 clocks, it's going to do what the other thing took like 250 clocks to do, because it had to resolve a lot of math and do other stuff in high-level language. So this is going to be faster. So when we run this, I'll do a Control F10. It's running now, and I think I want to say like, well, let's see, we can figure it out. If we're 300 megahertz and we're 6 clocks, it's 50 megahertz. So it's taking about 5 microseconds. So instead of 200 microseconds, it's taking 5. So it's about 40 times faster. And that can be the difference between, you know, assembly and spin. Although spin is a lot faster than it used to be, but when you get into doing a lot of math, there's a lot of math pushes and pops on the stack, and it slows things down. So here, I mean, this is 6 clocks of the same function in smaller, faster code that runs directly. Any questions on this? All right, I'm going to go to the next thing.
Actually, I have a question. You say that the line where
It, right?
pin mode is
Now
set,
you do this on the other side.
that you are setting just those XXXX values. Why does where pin just set those XXXX values in mode? So
Well,
they write mode, where pin mode pin. You said it just writes those those XXXX values in mode. Why?
because this is like the low level pin configuration. It doesn't even have anything to do with smart pins. So that's why we don't use WX or WY for this, because we're just looking at, we're just talking to the low level smart pin that is the pad, the custom pad on the chip. So it's not engaging anything else. It's just setting up the lowest level configuration for the pin. Does that make sense, Mike?
So where pin on a mode will always set those bits and none of the other ones?
Well, it's because of the set byte. You see this instruction? So byte 0, if this is comma 1 does this. If it was comma 0, it would do these bits. If it was comma 2, it would do these bits, and if it was comma 3, it would do these bits.
Okay, I didn't recognize set byte. Okay,
Yeah,
nice
that's
instruction. Nice instruction. Yeah.
yeah. It just pokes the data where you want it, and so you can see there's not much to making a DAC high. So pin is 8, right? Pin is 8, so we just make the pin high, and we write pin with the DAC with the DAC mode and the 8-bit value, and the pin goes right into DAC mode and outputs that analog value. There's just 2 steps, really.
I think the other assumption there, Chip, also is that set byte, if I'm correct, works with the least significant byte of the long, right?
Oh, yeah, that's the other thing, yes. So it's gonna, so level, so this is the destination, right? It's gonna put it into mode, which is this guy here, which is this value. So that's the destination. The source is level. And so when it says comma 1, it's gonna take from the LSBs of level, the lower byte from level, and it's gonna write it into byte 1 of mode. Does that make sense?
Thank you.
Yeah, now it does. It's funny how short things get in P2 assembly.
Yeah. Yep.
Well, that's why I'd like those comments there in the spin code. More questions for Chip. It can't be that easy.
Oops. Can I speak?
Yeah, please do.
I came late, unfortunately, and I didn't. You must have introduced the DACs previous to my arrival. I was wondering, are the DACs pulse width modulation DACs?
No, I'll show you real quick here. I have a little. We'll go over
I'm
this.
very sorry. Yeah.
Okay, they're very simple. This is it. It's just a resistor summing system. So we have like some thermometer logic. We have 255 of these things, and they just drive high and low and sum together. And then there's some thermometer logic that determines how many are low and how many are high.
What do you mean thermometer? What did you say?
So like, yeah, you know how a thermometer goes from, it goes like the indicator liquid goes from, it goes upwards, right? So it's solid, and then there's vacancy above it. And that solid, where the top level is, moves around.
Yeah.
Well, that's how it works on this. So we have an 8-bit data that gets fed into the DAC, right? And so this first inverter will go high if that 8-bit value is greater than 0. The next one will go high if that value is greater than 1, and then greater than 2, and then all the way up. And then here we have the last 3. This one turns on if it's greater than 252.
You mean to say that there are actually 254 resistors feeding a output?
There's the equivalent of 255, yes, but they're grouped in so that there are 16. What we did is we have a 16 size resistor, and that's controlled by a single thermometer bit of logic. So we have 15 groups of 16 which are treated as one.
Aha.
And
I
then
see.
we
So,
have an 8, 4, 2, and a 1 equivalent.
well, Chip, I'll look forward to looking at reading your documentation to see if I can finally understand the thermometer.
Well, just imagine it going up and down. So at some point, you take any inverter in this thing, everyone, if that's where the level is, everyone below is outputting a low, everyone above is outputting a high. And that level, that midpoint moves around depending on what value you write. So you have like a tug of war going on. Some guys are outputting low, some guys are outputting high, and those resistors.
And what's the, how do you manage this kind of, activity electronically? What is the circuitry?
It's just like this. It's this
Just like that.
Yeah.
I'll have to scratch my head about this for a while.
Because when you design like hardware, you're very conscientious of, well, how many chips is it going to be? How much wiring am I going to have? But when you're doing a chip, you can have thousands of everything. It doesn't matter. It all just resolves down to some amount of area.
Yeah, well, that's fantastic, and I look forward to understanding it even deeper in the coming days and years. Thank you.
Yeah, you bet. Well, you see the point of this topology, it's very simple, so it's very fast. It settles in like a couple of nanoseconds.
Fantastic. And how accurate is the 8-bit DAC?
It has inherent linearity. It has an inherent linearity of about 10.5 bits.
I see.
Okay, but it's an 8-bit DAC. It's just an 8-bit DAC.
Is it monotonic?
Yes, absolutely.
Yeah. Mm-hmm.
Yeah.
10 bits, yeah.
And
so,
see, this is so simple. If you were to try to put any kind of analog feedback loop in there, some kind of op-amp, you'd destroy its quality. This is so dumb and simple. It just works. And you see where we have all these values on the left? Those are actually flip-flops. So all the decoding is done beforehand by flip-flops, so that when the clock rises, all of these update in absolute parallel time.
I see.
So you very quickly.
It sounds as though you've found another very ingenious solution to a basic problem. It's very, very nice. Thank you.
I think this topology is probably the oldest DAC topology around. But when you're designing chips, you can do stuff like that because it just becomes area, you know? All it is.
How many DACs do you have? I'm sorry, I never...
There's 2 in each pin. There's a 990 ohm DAC and a 124 ohm DAC.
What do you mean 990? What do you mean the ohm DACs?
Okay. The thing about this kind of topology is you have constant impedance, right? The impedance doesn't change. Okay. Which is important for RF signals. So you could turn this RP resistor on in this bottom mode 1-1, and you actually get 75 ohm 2.0 volt output.
I see. Very nice. Yeah.
It's so simple. Totally. The best things are the simplest.
I wonder if you have an example where you take one of your ramps from a DAC and then put it into one of your A to Ds. Then
we're gonna do that.
Okay. Well, I'm looking forward to all the good examples. Good.
Yeah, I've got that here. Any more questions on this? This is assembly.
Yeah, I'm saying they couldn't see much of it because it's gonna go dead again.
It's okay, just take it for veg.
Okay, Chip, quick question from Facebook from Alberto. Can I generate sine waves adjusting the level variable and using a sine table or something like that?
Yes, we have that today too. We got it already.
Oh, wow.
Yeah.
Okay.
Okay, so
proceed.
I'll move on. Okay, so now I'm going to go to DAC 4. Now, here we have the pin is now 8 with add 3, right? So we're going to do 4 total. So just like the ADC, you can set up DACs to be in parallel too with these kinds of things. So we're going to start the scope up again. I've got pins 8 through 11 wired to 0 to 3. And we're We're going to make all those pins outputs, and then we're going to give each of them a separate value. So we have I that's incrementing, right? And then we're going to do these 4 different offsets. Okay, so we have to do all these things separately because each gets unique data. So each needs its own write pin. Okay, so when I run this is really nothing that you haven't seen, but you're just seeing 4 at once with these different offsets. Okay, so you can see the green is 0, and then the red, I think, is 1, and then the blue is channel 2, and then the yellow is channel 3. And we could make these things, we could make these offsets smaller, right? I could make them almost touching, only 1/16 the difference. But anyway, we can control all these things uniquely. We can configure them at once and then feed them separate output values. Any questions on this?
Chip, I've been afraid to ask a question. Could you use decimal values instead of hex if you wanted?
Well, not really. I mean, you'd be getting into floating point then, which will slow things way down. Most any problem can be addressed in fixed point like we're doing here, or just, which ultimately boils down to integers with maybe imaginary, separators.
So
But
you could use integer decimals, just not floating point decimal.
Yeah, that's what I wanted to know.
Instead of hex, you could have 0 and 255 there.
That's my question, Roy.
0, 0, and FF.
yeah. I mean, I could, yeah, these could be anything. Like we want to offset them. Let's say we offset them each by 10.
Yeah, that's a lot easier. I might have the only hexadecimal learning obstruction here.
Yeah, there we go. Now they're all
Thanks.
offset by
That's
10.
cool.
Yeah, you just haven't been coding long enough, Ken. Us old timers, we think in hex.
You guys do. I'm too busy doing the wrong end of this job.
Okay, let me
People go into octal.
I'm going to quiz you tomorrow, Ken.
I'm already afraid, John.
I'm going to put this back so I don't lose it, right? So when I say, okay, so now I'll go on to the next thing here. The next thing was, so here we have our smart pin mode, okay, which can take that 8-pin DAC and 18 bits by dithering between 2 adjacent levels. So what I'm going to do now, this is different. This was 1x on everything heretofore, but now I've got it set for 100x magnification. And what we're going to do is we're going to observe the DAC climbing between, remember, it's just an 8-bit DAC, right? It can't output any fractional value, but by dithering in time, it can average out to really anything that's sub-bit. So we want to look at it magnified, and we're going to output something right near the midpoint, right? And we're going to go up 3FF. So if you add 7F00 to 3FF, you're going to get what? 82FF. Is that right? So we're going to go from 7F00 to 82, or to 82FF. Did I do that right? Roy, you should know.
Sorry, what?
Yeah.
We're just going to step a few things. So what's going to happen is the DAC is going to dither between 7F and 80, and then it's going to dither between 80 and 81, and then 81 and 82, and then 82 almost to 83, and then it's going to reset. And we are using the PWM mode here. Now we have 2 ways to do this. We have a random noise mode where it dithers the DAC randomly, between 2 values, and we have the PWM mode. If you want better linearity, use the PWM mode because there's only 2 transitions per frame. There's either 0 or 2 transitions per frame. If you want, but what you have to do when you use this mode is you have to have a an update frame that is a multiple of 256, right? So that you don't interrupt any of these little timing subframes. Now, if you don't care so much about linearity and you don't want to have, you know, some even time division like 256, you can use the dither R&D mode. And what this will do is it'll instead of adding an 8-bit counter to the LSBs of your output value, it will add a pseudo-random number that's always churning. And it will more quickly settle on the analog value. But because there are more transitions, you're not going to get the depth of linearity that you get with the other mode. So I have this first line. They have the second line commented out. I have this one active, right? So let's see. And we're looking here. 8,000 means this is the max speed. We're going to have a sample on every single clock every 3.3 nanoseconds. We're going to get a sample on the scope. And it's going to be magnified, and it's going to reflect this business of this PWMing. So down here in the loop, I do here we start the pin up, and then we do a write Y pin to talk to the smart pin. This isn't talking to the low-level DAC circuitry in the pad. It's talking to the smart pin. It's saying, here's your new output value. And this could range from from 0 to FFFF. Actually though, yeah, you know what though? In 16-bit mode, you really can't go above FFOO because there's nowhere to dither further to. FF is the limit of the 8-bit DAC. So you can go from 0, 0, 0, 0 to FFOO. Okay, so what we're gonna do is we're gonna update the DAC with a new value. We're going to then wait 20 milliseconds, and then we're gonna increment that value. So here's what happens when we run this. I do a Control F10. Now this is what you're seeing there, the low and the high are adjacent 8-bit DAC output levels, right? You see what that's doing? It kind of climbs up and then reaches the plateau, flattens out. Then it starts to climb again, reaches the next plateau, flattens out. So what you're seeing is the dithering between two adjacent 8-bit levels. And the order of time here it's doing a whole 8-bit frame in less than a microsecond. So if the clock's running at 300 megahertz and it takes 256 clocks to you know, output one of these subframes, then you're getting about 1.2 megasamples at 16 bits. So do people have any questions? You guys understand what's happening here? Why you see like a little lump occurring and then it kind of like goes all the way up and then it flattens? Whenever it flattens, it's hit like an integral 8-bit DAC value. And then as it starts to lump up, it's because it's going a little bit beyond that towards the next level. And then eventually you get little nodes pointing down and then it levels out. So this is the best linearity you can get out of these DACs.
Yeah, it'd be nice if you could show a line that was the average, because then you'd see that line swooping up smoothly.
Well, that's
the average.
That is next. Watch this. When we switch over to the R&D mode, well now, rather than like, you know, having a contiguous set of lows and then a contiguous set of highs and they summing to 256 clocks, now it's going to mix those things up randomly. So those zeros and ones are going to be spread evenly throughout this thing. And you can update it any old time you want. So watch what happens when we run it this time. There's some.
Yeah, it's still got the noise. It's just more noisy. I'm saying if you had a mode that could show the average of the whole line,
yeah,
that you're currently showing as a straight line, then you would see that line moving very smoothly up.
Right.
You know, with the averaging.
Yes. Yeah, I don't have, you know, that's something I can add later to the debug stuff. But what you're seeing here, you know, it is sampling, and this is going through just 64 flops in this filter that's in the scope mode. So it's really it doesn't really have more than 6 bits of resolution in this mode, or not much more than 6 bits.
Sí,
But
pero
you can see
empiezan
that,
antes.
we'll say that again. But you can see it's averaging, you know, pretty quietly there. But most of the mess we're seeing is because
Okay. Eso que yo hablé, yo lo escucharon.
we just don't have the resolving power. But this is happening fast. This screen
mi micrófono.
is like 1.6 microseconds worth of signal.
Chip, a question for you.
Yeah.
Could you explain the math in the right Y pin?
Explain the what again?
Your addition and then the ANDing. How do those values make sense?
Okay, you sound kind of muddled, but you want me to explain what values make sense, like what these do?
Correct.
Oh, okay, all right. So we have this thing set up for super high magnification. At that point, we need to be midpoint output because the ADC at 100x magnification wants to see a signal that's near the middle of its range, and it will resolve it. So what we have here is we have this value 7F00. Remember, that can go all the way to FF00, right? But at 7F00, we're midpoint. So we're in the sweet spot of where the ADC can actually read it. So we go from 7F00 to that plus 3FF max. So let me pull the little calculator out here. If we go, you know, 7F00, whoops, hold on, hex, right? And we climb up 3FF from there, we go to 82FF. So that means that our DAC is going to be dithering up to 83 towards the end, and it will start at 7F. So what we're doing is we're giving it a ramp, but over the span of like four discrete 8-bit values. You have 7F, 80, 81, 82, and 83. There's actually 5 discrete values there. Or no, it should be 4. 7F, 80, 81, 82. Yeah, and sometimes it jumps up to 83 during dithering. And see, I could make this.
You've got a, yeah, I'm missing it looks like you've got, you're limiting I to 10 bits.
Yeah.
And then you're adding that resultant value to 7F.
Yeah, which is like an offset, a coarse offset to get us into the range of the ADC.
Gotcha. Okay.
So for understanding, there should be I and 3FF will be resolved first, and then
order of operation.
Typical math operations. Yeah, so it's you have to imply the precedence without the parentheses. Yes.
Oh yeah. I'm sorry. So yeah, the precedence here. Yes. We have really nice precedence, but it's complicated.
Yeah, I usually tend to make columns around everything. I mean, parentheses around to make sure that I get what I get. Normally, a compiler will kind of sort it out anyways.
So, I mean, I could let's say we make this just FF, right? And we go back to this first thing where we're using the PWM. You're going to see it toggle between, in fact, here, to do that, let me make this 80. Okay, so we're better in the range here. So it's going to toggle between, whoops, that wasn't right. It's going to toggle between 80 and 81. So you see, it's almost all 81, then it resets. So what we're looking at here on the bottom is the 80 output from the 8-bit DAC, and then the 81 output is what's on top. So we're just toggling between these two things. Any questions about any more about this?
Chip, I have one.
In your scope output, you should make it able to put a scale on the side that you can see the number of the values?
Oh yeah, I'll do that someday. Yeah. Right now we don't have it. Ryan, what were you gonna say?
Yeah, I was gonna say on that sweep that you're displaying right there.
Yep.
Is that 1.6 microseconds from peak to peak, or is that the time sweep for the entire display?
From left to right.
Okay.
From left to right. It's let's see. Let me go to let's see. We've got 300 megahertz, right? And this is 256 clocks, so 256 divided by 300. So it's 850 nanoseconds. Oh, no, excuse me. There's 512 samples. That's why we're able to see 2 whole cycles of that. So I got to multiply this by 2. So it's 1.7 microseconds from side to side.
Okay. Huh, that's very fast.
Yeah, and it's coming in through ADCs on some other pins, which are filtered with like a string of flip-flops and then well, it's called what kind of filter is this? It has like curved side lobes. So it's making the most of what it can get out of 72 bits that have come out of the Delta Sigma ADC in series. So there's like a sliding window of 72 bits, and it's filtering them to make these 8-bit samples we see here. So in the future, I want to make the ADC faster, and this will sharpen way up. But what we have is actually quite good for audio and video too. Video is much more demanding.
You don't have to have any onboard capacitance to smooth it out?
Well, here's the thing. The capacitance is kind of virtual because as these bits come out of the ADC, they're just zeros and ones, and the proportion of ones to 0 indicates the high or lowness of it. So if those bits slide through, they're each given some weighted value, and then they're all summed together. And that creates the analog value that you see here. So this is a really high-speed ADC mode, but it's not the most accurate. It's just good for looking at super high-speed waveforms.
Is your dither random? Is that a hardware implementation?
Oh yeah, yeah. Let me go back to the random dither. Yeah, it's all in hardware. We have a 128-bit, really nice pseudo-random thing that we seed with noise on startup.
Okay.
And it carries on after that. And so here we have using just random. It looks a lot more linear in slope. Oh, you know what we could do? Watch this. We could slow this thing way, way down, right? We could go like, in fact, we could even go slower than that. All right, this will take a while to queue up, but this will give us kind of what, well, not really what Roy was asking for, but well, I wonder how long, there we go. Look at that. So here we were taking, our sample rate was super, super low. I mean, it took that long to fill that, but we're moving the DAC very slowly too. But what you're seeing there is the linearization of 5 discrete steps of an 8-bit DAC. 7F, 80, 81, 82, 83.
And Chip, could I draw your attention to a question in the chat from Dustin?
Yeah, of course.
He says, so what actually is happening? Is that peak getting wider and wider? If we were to sync it up, like also give it a trigger, we'd see it growing like a PWM square wave?
Yes, yes. But see, that dither is 48 dB down, right? Because it's an 8-bit DAC and it's toggling 1 LSB. So that dither noise is way down there, and it's at a very high frequency. It's at the clock frequency divided by 256. So for practical purposes, if you're using this for like an analog DAC for audio output, that is just going to be filtered out in the signal chain, and you're never going to notice that slight noise pattern. You'll never notice it.
Is that noise a normal distribution?
That you're seeing on the screen right now?
Yeah, it looks like it probably is, but it's.
Well, it's,
Yeah.
I mean, these are just samples that were taken at discrete points in time. If they were averaged, that thing would look way cleaner, but it was just a sample that was taken at some point in time and they were all put together. And then that thing only has about 6 bits of DC resolving power. So what you see, you should expect to see 1/64th of full scale, you know, just noise. And that's
I see.
about what we have there probably. Yeah, so by slowing it down, we can see. In fact, let's do this. Let's make it just go from, just do 1 bit. And I think we can speed this up. Let's go. So here it is. Oh no, it needs to be slower than that. Hold on. In fact, hold on. Let me do one other thing. Let me lift it up just a little bit. Okay, so when this thing updates, we're going to see what happens between outputting 8000 and 80FF, which is really, it's just going to dither between DAC values 80 and 81. So there you go. That's what the that's what it looks like going between 2 adjacent values. And if we had averaging, that could look a lot better. Any other questions on this stuff?
Chip, I had a quick question when you were doing just the non-smart pin DAC mode.
Yes.
When you have all 8 bits filled with ones, are you getting 3.3 volts out?
Absolutely, yeah. That's rail to rail.
Okay, so there's no level control there. It's
No.
3.3.
Right, yeah, just think what happens. This is all 3.3 volt logic here, right? So when all these things are outputting highs, you're gonna get a 3.3 volt high out of here. Now, if you turn this RP on, you know, you can knock that down depending on what mode you're in. Well, you knock it down to 2 volts. But yeah, it's all rail to rail. The output is rail to rail. It's the input that needs calibration, or the ADC. Anything else about this? I've got one last thing here. Let me make this just how big is this? Okay, what this is, it's the same kind of thing. We're pulling in scope. I've got these same pins connected. We're going to output on 4 pins. And what I'm doing here is this is what we do for the low level setup, right? But in the case where we use, and this isn't the right name symbol, it's the right value, but it's not the right name symbol. Let me see if I can find it real quick. What should this symbol be? Hold on. It should be key channel. Okay, so for this context, it's the same value, but that should be the symbol right there. So what we're saying now is we're going to configure the DAC as this, you know, rail to rail, low impedance, high speed thing. We're going to make it an output so it's on. But then because we set this thing here, it's going to become a COG DAC channel. And the COG that we want it to listen to, we have to install here. So instead of installing a full 8-bit value, we install a 4-bit or a 3-bit value, and that tells it what our COG number is. So this, once configured this way, anything that goes out on the DAC channels will appear on every set of 4 pins. So we're basically like it's like turning it onto a channel. We're gonna listen to COG, whatever COG this is. It's probably gonna be COG 0. And this thing here, this first bit of code, this is inline assembly. It makes a table that has a sine, a cosine, a ramp, and a square wave. And then down here, we're going to use the streamer. Oh, the table gets built into the LUT memory, okay? And the nice thing about LUT is you can pull data out at any, you don't have to go sequentially. You can have a counter with a numerically controlled oscillator to grab data anywhere in the LUT at some pace. So here we do a little bit of FMing. We add to our R value, and then we rotate it, and then we get it, we add it. So this is creating an FM, like a frequency modulation. And then by doing this set cue here, we set the frequency, and then we tell it to output in DDS mode, direct digital synthesis mode. We're actually doing more than is shown here. I borrowed this code, but I'm going to run this. Let's see what it does. Okay, so someone was asking last week about, can you do a function generator? Well, here's one. So the LUT, because I moved it, I messed up the timing. Because the LUT has 4 bytes and each DAC channel is 8 bits, it can output 4 concurrent 8-bit channels live. And the period on this is, what is the period on this? It's not super high, but it could be very high. But I slowed it down so that we get nice crisp edges on the square wave. We're not seeing the filter do its thing. But what we've done here is we've loaded up the lookup table, which is 512 longs with 4 sets of bytes. And then we're outputting those bytes. We're flying through the table, and it's all happening in the background. We don't have to do any work. And it's grabbing those longs, separating them into 4 bytes, writing them to those 4 DAC channels, and then we get to control the numerically controlled oscillator via the set cue instruction. And then up above here, we compute what that is. So if we don't want, let's say I want to go max speed here, right? Oh, it's so high that it's being attenuated by the ADC. But let's do this. Let me just put a value in here like,
Chip, in terms of resource usage here,
oh, it's still too small.
Just 1 cog?
Oh, wait, you know why? Because this is 512 steps. To get it to go through every step, we need to use this number here. Okay, now, but it's just, it's 1-to-1. There's no FMing now. But you can see all 4 functions there. Let me put it back the way it was. Okay, what's that, Ken?
I was asking about how much of the P2 resources are being used.
Just a cog, and its LUT is holding this data table with these 4 waveforms in it, and then this little bit of code is running. I mean, we could right here, if we put FF
and 4 pins, right? 4 smart pins, or
yeah, 4 smart pins, right? And I could just say jump in a loop here. Oh, wait a minute. See, why did that not work? That means do it infinitely. I'll have to, I'm not sure why that didn't work, but wait a minute. Did I have 1 here? Uh-oh, I think I busted it.
So Roy, is that cog busy telling the smart pins what to do, or did he just set them up and let it go?
no, he's got that little loop there that's making it expand and contract the waveform. But if he wasn't doing that, he could be doing something else entirely with the cog, because it would display the waveform. But he's changing the frequency by doing this loop with the set cue.
Yeah, I mean, what if I just put it, gosh, why is that locking up? It's like it's not getting the right frequency at first. But I don't need, all this loop is doing is just changing the NCO frequency for the streamer. It's not really involved in outputting that data at all.
Chip, in the 4-color ARB output, why the differences in amplitude between signals?
in this one here?
Yeah, I think so.
Yeah, they're slightly different. It's sort of averaging out the voltages.
Yeah, it's because of the filtering. Watch, if I slow this thing down, right? Like if I go, it's the filtering that's done in the smart pin for the scope mode. So if I slow this thing way down, and then I slow down our scope as well, they should get.
Yeah, they're a little closer, but the sine waves
Here.
still clip shorter.
Yeah, I'll even make it. There. Now we don't have much FM going on, but by making it slow down, we have more dwell time in that filter, and so we get peaks, like sharp peaks come through better. Let's see here. Why isn't this thing FMing much?
So Chip, if it's the filtering, how does the programmer account for that in software?
It's just the ADC, the fact that he's reading it back, that's the filter.
Right. Yeah,
the actual output voltages are going all the way to the
top.
It's just the ADC scope mode that's sampling it is filtering it and rounding them off.
Right.
The square wave is always all the way up there because it's sitting at its peak value for the whole time, and then at the low value for the whole time.
Thank you.
There's the ones that are sine or triangle get rounded off.
Right.
Okay, then another question from Dustin. You can see it there, Roy or Chip.
Oh, let me look. Let's see, I don't see the chat here.
So the waves are in LUT and the streamer is reading the LUT to tell the smart pins what to output?
Yep, exactly.
Right. Yep, every cog has a streamer, and every cog has a set of DAC channels. And you can have the streamer just spew data that either gets from the LUT at random access points based on an NCO, or sequentially from hub memory, or even from, I think it can even do from IO pins coming in. You can stream all this into your DAC channels, and then each IO pin can tune to a certain cog's DAC channel. So like pin 0 is going to be channel 0, but for any of the cogs. Pin 1 is going to be channel 1, but for any of the cogs. And then when you channel 3, or pin 3 is going to be channel 3 for any of the cogs. You can pick which cog channel 3. And then when you get to pin 4, you're back to channel 0 again. So each cog can output 4 discrete channels. And there's also a set DACs instruction for when you're not actually using the streamer to feed the pipe. You can just do a set DACs, and in a 2-clock instruction, you can write all 4 bytes to your channels, and that will be reflected on any DAC pin so configured.
To clarify, can you configure multiple pins to the same cog channel, so you could drive from one cog's 4 channels, you could drive all the IO pins?
Yep.
But they'd be repeating the same output. It would just be different pins. Yeah.
But you could get a lot lower if you want to get like way below 75 ohms impedance. You could do that, right? Because you could tie those DAC outputs together.
Yeah, and get lower impedance.
Yeah, you could get super low impedance. I mean, you could drive 8 ohm speakers, and you could also. There are DAC output modes with the streamer where you can say like output just the byte 0 from the LUT to all 4 channels. There's lots of combinations like this so that you can gang these things together and make really low impedance analog outputs.
You could also fill the LUT with a different piece of code to make the waveform change over time as well. right? You could just
Yes.
constantly update the LUT with a wave shape, and the streamer will be outputting it to those DAC channels for you.
Yes. Yes. And there's also there's a color space converter. I want to show one other thing. Any more questions on this? Okay, I'm gonna.
Yes, just one question. When you, for example, the example you've just given of 4 DACs outputting different waveforms, does that suck a lot of power from the power budget for the entire P2?
Only for the I/O pins. So
yeah,
just the DACs inside the I/O pins are going to draw current, right? Because of their constant impedance mode, they are loads unto themselves.
Yeah.
And so that takes some power. But if you drive them with 0, 0 or FF, there's no DC.
How about if I had, for example, the same example you gave us for all 8 cogs? Would that be, would that overheat the P2?
No, it will get a little warm. I mean, we can figure that if we have, let's see, where'd that one drawing go? Let's see, where'd I put it here? If we have, let's see. Let me look. Okay, so we have 31.6K. So in the worst case, see, you want to use these higher impedance DACs if you don't really need low impedance, right?
I see. Yeah. Okay.
But if you want the super low impedance, it's 31.6K. So 31,600 ohms divided by 128. You're 246 ohms. So having that thing output a mid-level value would be like
yeah.
that over 1.8 or 1.65. So it would be like 6 milliamps
per channel.
Yeah. Yeah.
So 6 times 32. That's a lot of amps.
Yeah, times 32. It's gonna, yeah, it's 1/4 of an amp. Yeah, but you know the core at 1.8 volts eats. It can eat upwards of an amp if you're really running everything full blast. So this would be on the I/O pins, right?
Yeah.
And so yeah, it would contribute to heat. That'd be 1/4 watt, but or no, actually that many amps times 3.3 volts. It'd be like 0.7 watts.
Yeah. Interesting. You have to learn, but the P2 is really a living animal that you have to live with and figure out. And
if you push everything to the max, you can get it quite warm. Mainly if you push everything to the max and run it at a high clock frequency.
Yeah.
Like if you stay down at like 120 or 150 or something, you could probably push everything to the max and it will just get warm, right?
With that many cogs, it's amazing what you could do. And if you really exploit, but imagine using all that power. It's just mind-boggling how much you could do. So my question was actually purely rhetorical.
Yeah.
Yeah.
Yeah, there's so many things that we have yet to explore as far as applications go.
Yeah.
Here is a little thing that comes in the distribution file. It's just called VGA text demo. And let's go into one of these files here. Let's see, HDTV 19 text 135 by 160. So here is a program which generates HDTV signaling. It's a little object. It even has a font built in, right? So, but the business part of it, here's some data that it uses. This here is the business part right here that does all the rendering to the screen. they're from field loop down to here. I don't know, maybe 60 lines of code or something. But this uses the color space converter, which here it configures it. It's setting it up for HDTV type signaling. But watch this. So this uses the DACs, right? And what it's doing is getting characters out of memory and then translating them into pixel patterns to make up a character set, which then outputs to video. So VGA text demo, let me go back to here. So here's our little program. I'm gonna run this. Now there's nothing debug, but I'm gonna have to, let's see, I'm gonna stop sharing now. And I'm going to take this, and let me, got my big TV here. I'm gonna switch this over to component. So look at that. Let me get some perspective here. It's in 1 second, it's scrolling through like an 80 kbyte thing. This is all happening on the P2. But this is a 1080p display, but it's turned sideways. So I made the driver so that it has to render all the character stuff sideways. Let me see if I can get in here where it, there's so much, let me dim the screen a little bit by plugging in something in parallel, which will lower the voltages a little bit. If I can make it dim enough, you might be able to see it better. That's a little bit. Anyway, this is signaling at, gosh, I wish I could get it. It looks great to me, but it looks horrible over this camera. But this is signaling pixels at 148 megahertz, 108.5. So that is that's
amazing.
That's 6.7 nanoseconds per pixel. I wish I could just get in there so you could see.
Well, we need a zoom driver for the P2.
A zoom driver. Yeah. Yeah. Oh, yeah. There we go. Anyway, and watch this. This is all done over 3 pins, right? You see this? Now watch. I'm going to pull the red. Watch the display. No, there went the red. Now it's very bluish. Now I'm going to pull the blue. And now we have a monochrome display. Man, it's too bad. It looks so terrible. But look at
got
this.
it. It looks good, Chip.
It looks horrible on my end, but
it looks very blurry, but it looks good. It's just a webcam blurriness.
Yeah.
Yeah.
Well, it's huge.
Yeah, yeah. It's a lot. But look at this. This is one signal. This is the beauty of component video. I unplug it, it's gone. Plug it back in. Whoops. Wait a second. Oh, let me unplug the monitor here. Oh, there it came back. So with just one DAC pin, one 75 ohm, 2 volt DAC pin, we can feed this entire 1080p at 60 hertz in monochrome.
That's amazing. Is the P2 fast enough to drive USB-C video?
No, because the trouble with that is we start getting into LVDS running up in the gigahertz, and we don't. You know, we could design a chip in the future to do that, but it involves making super high-speed shifters, SerDes, like are used for HDMI.
So does that mean it's completely like there's no point, or just if you want to do USB-C video with the P2, you need some support chips as well?
That's right. Yeah, I mean, we could generate the pixel stream in analog, but getting it into the SerDes format, the LVDS requires more hardware.
Okay.
They run those differential streams in the multiple gigahertz range, and we can't signal at the gigahertz range.
Yeah, at 180 nanometer, we haven't got what it takes. I'm going to select here. I'm gonna select another video driver. I'm gonna go to the 640 by 480 for the VGA. And now, see, where's my camera? You can still see this. So see, here's like a regular little old, I don't know how well you can see that, but I can't see anything. What am I looking at? Oh, there you go, okay. Anyway, this is using 5 pins. There's RGB and horizontal and vertical. And that's coming on this connector down here. It's too bad the analog stuff is going away because it works so nicely and it doesn't have the silicon requirements that this new stuff has. But anyway, these DACs are designed to be able to signal high-speed stuff so that we can do video and direct digital synthesis. And we haven't even really explored, I mean, we could easily make like an AM or FM transmitter. That's not a problem. Now that pretty much concludes everything I'd prepared, but I can answer any questions.
Yeah,
In
questions.
that sine wave, oh, sorry.
No, please.
In that sine wave, you were trying to get it to run, I think, without any code. The jump was just you weren't running any code, and the pin was doing it all internally.
Yes. Well, the streamer in the cog was looking at data up out of its LUT using a numerically controlled oscillator. So it was, the rate is 32 bits variable. And then it was taking the data from the LUT and feeding it into the cog DAC channels, which those 4 pins were then outputting. And all we were doing is playing around with the frequency of the NCO. But all of the lookup, all that automation happens in the background. We were just tweaking the frequency, but I could set the frequency and just leave it alone and just jump in a loop or have the processor, you could write code to do something else. You couldn't use the streamer, but you'd still have access to the FIFO for the main memory. You could write code.
I guess what I'm trying to differentiate here is you've got streamer, DAC, smart pin. What, how do you separate them as far as I'm just trying to wrap my head around what the difference.
Well, they're all separate subsystems. So the smart, well, the DAC on the pin is a custom silicon thing, and then its functionality can be augmented by the smart pin circuit, which is a logic thing, which can do like that 16-bit oversampling, and it can also, the smart pin logic can also feed it the DAC channel data coming from the cogs. So the streamer can compose this data and stuff it into these channels, and that's closely coupled with the cog. And then the smart pin can hand that to the pin to display the data. So they're just a bunch of subsystems that can be connected up if you do connect them.
So there's a DAC in every pin, and then there's a streamer for every cog, right? So
yes,
it's not,
okay.
There's
the
way it works is the cog is feeding the streamer from its LUT, and the streamer is then connecting those to the DAC channels into the smart pins, right? So it goes cog, LUT memory, into the streamer, out of the streamer, into the smart pin, the 4 smart pins that were designated as the DAC channel receivers for that particular cog. And then the smart pin then does the actual DAC output.
That's right. Yeah.
And the cog has nothing to do anymore.
It's out of work. It's been replaced by robots.
But once you've activated the streamer and it's reading the LUT memory, it'll just all go on in the background, but you can tweak the values in your cog. Like your cog code could go back and poke the pin to change values, which is what you were doing, to change the timing.
Yeah.
It could very easily have been doing something else entirely.
Totally, yeah. Yeah, so the LUT was kind of on autopilot. We were just changing the rate at which, the streamer was on autopilot, and we were just changing the NCO, the numerically controlled oscillator, for how that controls how fast, or not how fast, because it happens on every clock, but at what the streamer steps through the lookup table, the LUT memory. And we were just changing that rate. We're just kind of turning a knob.
I've played with it a little bit. The code you gave me a month or so back for sine wave generation. Been playing with the LUT a little bit, trying to get custom waves, and it's a lot to take in.
Yeah, it doesn't. If I could, I need to write, like always, I got to write documentation, but it's all digestible. And there's nothing hard about it, but I don't think we have the picture congealing yet. But it's really just a bunch of simple stuff that you can use together.
Yeah.
There are different ways you can compose the data. It's easiest just maybe spin to make your lookup table, and then turn the streamer on. Oh, but you know what? Here's the thing. You have to run the streamer in another cog because for that kind of an application, because it wants to use the LUT, and so the spin interpreter uses the LUT, right? So that's why you'd want to, and why I did in this case, launch it. Well, no, actually, when that thing took over, it just kind of wiped out the spin that was going in the background, and it just took control of the cog. But if you want to have like a real application, you probably want to start up a cog and have it run some assembly language to operate that streamer, and totally use the LUT, which you can't use if you're using spin. We kind of need some kind of like some sort of recipe guide, like here, if you want to do this, you can do this in spin. If you want to do this, you're going to need to dedicate a cog because it won't be able to do spin also. So there are some things like this that probably aren't clear. And these could be impediments to people getting things working.
Yeah, and don't worry, Brian, like I've been closely trying to figure out the smart pin stuff for months, and I still feel like I've only got the tip of the iceberg. There's so much there, and there's so many options that can be configured together and interact with each other that isn't documented, that Chip needs to disgorge out of his brain into a document for us.
Well, it's actually all there. It's just that the dots aren't connected. There needs to be some like high-level diagrams of.
That's what I mean. Like you've given us all the low-level bits, but we don't know how they all work together very well, and we need that higher level. Hey, turn this on and turn that on, and then they work together and they do this.
Right.
I propose a Vulcan mind meld.
Well, I can't remember. You know what? I don't remember this all. I have to go back to the main document I wrote and review it to get my details straight. Because I put everything in there, but I can't remember them all at once.
Yeah, because there's so much in there, you can't wrap your brain around all of it and keep it all and do anything else.
Yeah.
To like reload it all bit by bit, and
yeah, you have to.
We needed to do that starting tomorrow.
Hey, Dustin asked, does the spin interpreter use the streamer itself to grab code? No, the streamer is not in use, but the FIFO is. So the FIFO is another subsystem that can grab 32 bits to or from memory on every clock. So in what I just showed you, we used the LUT, but not the FIFO. The streamer can pull data to and from the FIFO. But in the case of running spin, the FIFO is used to fetch the byte codes, but the streamer could be used. Well, what can you do with the streamer? Hold on, because the streamer always wants to either use the LUT or the FIFO. But there actually are some streamer modes where you just hand it like, you know, discrete chunks of like, you know, 32-bit values, and it does something with them. So you could use the streamer in those modes, but you can't use the streamer during spin if it uses the FIFO or the LUT, because spin is using both of those.
To be clear, you can't use it in the same cog, but you can, with spin, start another cog that then does the streamer for you.
Right. Right. Well, what I think we need are probably lots of like we need some good diagrams, and then lots of little bite-sized examples that help introduce all these pieces, and then you can see how they tie together.
Yeah, you need like the little sample program that shows you how each one works, but then also how the interactions between them can work.
Yes.
That's where it starts to get really interesting, and the combinations get really complex with what you can do. And that's where we don't understand it all, and we need you to help explain it.
Yeah, I hear you.
Well,
Okay.
Bill, I want to thank you for giving me that code. I mean, it was a month there, and I'm still pouring over it and still sinking in. I don't think any amount of reading material is just awesome. I mean, a few lines of code and it's doing all this. I don't know how you can write it out to make my brain understand what it's doing.
Oh, you know, if I didn't know about this, I'd be thinking the same thing you're thinking. I've just been working on this for so long that I know it. But if I were coming into this from the outside, I'd have it'd be the same.
But it works great. I mean, so far I've generated 110 volts out of 3 9-volt batteries.
Oh, awesome.
Yeah.
Hey, Chip, samples can be stored in the LUT?
Would say that again?
How many samples or bytes, I guess, could be stored in the LUT? Is that allocated to normal RAM, or how does is that
okay.
a area?
So the LUT is 512 longs, right? So you can have, and each long stores 4 bytes for purposes of sending to DACs. Now, when you set up those LUT DDS, direct digital synthesis modes, you can actually say, in fact, I had the docs up just a bit. Let me see if I can grab them. You can actually say from what range to circulate within the LUT. So there are some mask values that you can set to have it just, rather than fly through the whole LUT, you can have it go, in fact, here, let me share real quick. Share.
And just to clarify, there is a LUT per cog. Each cog has its own 512 long LUT memory.
Let's see here. Here we go. See this table here?
Yeah.
So when you set up that DDS mode where it's going to cycle through, you can specify what NCO bits from the top it's going to be using to do your lookup, and then what the loop size is. So you can set, so you can have like 32 different 32 long tables in there. And then like we were controlling the FMing, you could be switching between tables. You could do all kinds of stuff. So what we were using mode 0, we were using this, you know, just give us the whole thing. Actually, this right here. We were using this right here. I'll be out. Okay. So we just gave 0, but if had we given a non-zero value, like if we had given it this, we could have selected which of which of 16 32 long tables we wanted to access, and by controlling these bits here, we could give it a phase offset within those.
Okay.
So you can do all kinds of like signaling with this.
Yeah, basically you're just configuring the LUT to be either one big LUT or bunches of little ones, depending
Yeah.
on this configuration. And then the streamer will just loop over the smaller subsection that you've configured here with, you know, like if you selected the 100 one where it's 32 longs in a loop, it'll just loop over those 32 longs. And you can
Right.
select which one of the 32 long banks with the other bits there.
Yeah, with the A, we'll set which 32, which bank, and then here you can give it an offset. Like, what's the phase offset within that bank that you want to circulate in?
Right. So the initial read point within the 32
Yes.
longs. It's like saying start on the 14th long in and then loop from
Yeah.
there.
Yeah. Yeah, so there's lots of things that you can do that we're designed to be able, but you know, we haven't even really employed any of this yet. It exists in the silicon, but it hasn't been put to any use yet.
You have your little demo that just did 4 wave shapes to us. That's using it, right?
Yeah, that was using it.
Is it dividing the LUT up or dividing the longs in the LUT up?
That, what we were just showing was dividing the longs up. So for every long, there's always 4 channels, right? There's always 4 bytes within there.
Gotcha.
So there's kind of 2 levels of granularity. A long has 4 channels worth of information, and then the stretches of the longs can be configured, and you can change up that configuration every time you give it a streamer instruction, and it will like seamlessly from like the last clock of the last instruction to the first clock of the new one, it'll switch those schemes around. So you can really do more than just change. You can change everything with every single streamer command.
Does any of those divide the 512 long LUT up into pages?
Yeah, that's what we were just looking at here.
Yeah, so when you configure the streamer, you tell it, I want to treat the LUT as this number of pages, either 1 page of 512 longs or 2 pages of 256 longs, or and so on all the way down to however, you know, what is it, 128 pages of 4 longs, right?
Right, right.
And once you've configured it with what the page size is, you can then tell it which page to use and an offset within that page to start at.
Yep. And every time you give it one of those xcont or x0 commands or xinit, you can completely, you know, adjust all this kind of stuff.
Right, but a simple use case would be just
Right.
changing which page. So
Right.
like you could have,
Right.
you could have, you know, like you could use the 64 long one with a decent sample in 4 different banks, right? And you
Right.
could switch between those 4 in real time as you needed to play the 4 different samples, as it were.
Right. Yeah, and this is all in the main silicon doc. It talks about all this.
Yeah, you've basically made a hardware stream tracker that can play samples at super high frequency.
Yeah, it'll output each sample at the clock at 1 per clock.
You can configure the streamer to go at less than 1 per clock rates though, right?
Oh yeah, that's what that 32-bit NCO value is for.
Right, that's what I'm saying. So like you can slow it way down to audio frequencies if you wanted to, or you can run it super high.
Absolutely, yeah, you can go from, you know, synthesized radio, video, down to audio and below. Yeah, you have 32 bits of frequency control, so you can go down to like, you know, fractions of a hertz.
Yep.
Without going into it,
If you take a bank that isn't being used, let's say during the streaming process, can you write to that bank? So let's say if you have a bank and then you have one that's not active.
Yeah, there's a separate channel that the cog writes with. So if the streamer, I'm pretty sure of this anyway, because I know this came up during design, that you can use write commands from the cog to, no, absolutely you can do this. The only thing you have to be aware of is if you're writing to the same location that's being read on the same clock, because these are all dual port memories on the chip. So you can write to like a section and then switch over to that section and then modify, kind of like page flipping. You could certainly do that.
Yeah, and you could even write to the one that's being read. You just will get noise and jitter in your value if you happen to write to the one that the streamer is reading at that instant.
Well, it'll make up, there is some resolution circuitry in there in case there's that kind of read on write. It'll pass what's being written. But the trouble with doing that is that you don't know what phase it's in, right? So you're going to go in with your software and write it, and it's like you're going to hit it mid-phase and you're going to create some step function in your output waveform. That's why it's
so man, you'll create that step or jitter in your noise.
Yeah.
Chip, could you touch on sharing, LUT sharing?
Okay. So every cog has kind of a buddy cog, right? So 0 and 1 are buddies, 2 and 3 are buddies, 4 and 5, and 6 and 7. They all have a special relationship where they can receive each other's LUT writes. So in the way it works is you and your cog say that I want to receive writes that are going on in my buddy cog. And anytime that he gets a write to his LUT, it also gets done to your LUT. So you both have, so that way you have like a LUT, which is like a two-way window. If both those cogs set up the sharing, then they can see each other. Basically, they wind up seeing each other's LUT space. And I believe you can also, now you have to software control what part of the LUT is being shared. So there's no hardware gate on the portion of LUT being shared, but you can enable the sharing. It's just a 1-bit flag. There's an instruction called set LUTs, set LUT sharing, and it will turn that on.
So you're not actually writing the buddy's LUT. You're just writing yours and reading from theirs.
No, the way it works is the only control a cog has over is he can say, do I want to receive writes from the other cog? So when the other cog is writing his LUT, you get those same writes. So it sets up kind of like a shared memory effectively. Not that they're physically shared, but because they're both getting, like if it's a two-way street, then they're both whenever I write my LUT, I write yours also and vice versa. So it turns our LUT memories into basically like a shared RAM.
Yeah, so you always read your own LUT. It's just when you're writing, you either write to your own only or to yours and your buddy.
Gotcha.
Right. Yeah, and you can't control, like, am I going to write the other guy? No, he just has to give permission. And so any write you do, if he gives permission, will show up in his LUT also.
Yeah, it's the opposite of what I said. It's I'm going to receive writes from my buddy if I enable it.
Yeah.
Is that in that document you have pulled up there? Is that in one of those pages?
Yeah, let's see here. If I do this document, let's see, 4 of 5. Okay, let's see. Here we go. Yeah, RAM sharing between paired cogs. There it is. Yeah, so here you have it all. So this is in the main silicon dock.
Oh, so that's not in the assembly doc. Okay, that's why I haven't seen it.
Yeah, there are 3 documents we have. We have the silicon dock, which is this. we have the spin documentation, and then we have the, which also covers debug, and then we have the big instruction spreadsheet.
Yeah, and the one key thing to remember is that the pairs are fixed. So it's always, like if you're in cog 3, your buddy is always cog 2. Like you don't have a choice.
Right. Yeah, and there is a way to do a like a cog init where you ask for a pair of cogs that meet this criteria.
Right. So that you can coordinate to do the shared LUT. But you could also just start a cog and ask the cog itself, ask what cog it is, and then try to initialize its buddy and just error out if it can't.
Right. Right. So Jonathan asks, is there a way to only write to a partner's LUT without writing the local cog's LUT? No. I think what you want to have is like, I write, you read, you write, I read. But what you could do is, I mean, with the scheme we have, you can do that if you partition the memories and just say, I'm going to write this and you're going to write this. And you get the same thing. You know, you get 2 times 256 that way, but it would just be a decision you make in how you write your software. Oh, so he was thinking of daisy chaining processes from cog 0 to cog 7. Remember, this only works between adjacent buddies. Like even in odd pairs of cogs can do this, but you can't just go from 1 to 2 to 3 to 4 to 5, only between 0 and 1.
But wouldn't that mean that I could share from cog 0 to cog 1, and cog 1 then can share with cog 2?
No.
No. 2 and 3 are a pair, 1 and 2 are not. So 0 and 1 are a pair, 2 and 3, but not 1 and 2.
Yeah.
You always have one odd cog and one even cog, and they're sequential.
Yes.
Hey, Chip, is it
Yeah.
possible to stream from hub memory?
Okay, say that again. You sound kind of muddled.
Sorry. Is it possible to stream from hub memory like you can from the LUT?
Yes. Yes, but you don't have this random access like you get with the streamer. I mean, that you get with the LUT, because the LUT is like a private resource and you can control the address on every clock. But when you're dealing with the FIFO, it's all, you can set, you have 32-bit timing control, but it is absolutely sequential. You're not going to be able to like skip multiple addresses. It's going to be like just a matter of clocks between, you know, one data element and the next that are all sequential in memory.
Yeah, and just to be clear, it uses the FIFO when it's streaming from hub memory. So you can't do like spin or anything that uses the FIFO at the same time.
Okay. So if you were to play an audio file, like a WAV file, how would you go about doing that?
Probably load it into hub memory and stream it.
Well, if here's the thing, you probably want better than 8 bits for the DAC, right? So I would have the data in memory, and then just in software using PASM, configure some pins as 16-bit PWM type, and then when you can configure a whole bunch of pins in parallel for like DAC or ADC mode, and they will all run on the exact same time frame from when you turn their DIRs high. And so it's built into the silicon to be able to do that. So if you just had 2 channels, I'd turn them both on at once. And then every time their in goes high, you can feed it another sample. And those samples are double buffered. So you don't have to worry about, you know, getting the sample at the exact instant. You just have to get it sometime within the window so that it picks it up it starts to output that sample, and then you have a whole nother frame before you have to get, or you have that time frame in order to put new data in there so that it will pick it up. So if you picked up nothing, it's just going to grab whatever was there last time. But
okay. As long as you keep up with it and keep feeding it a new buffer.
Oh yeah, you know, well, audio, it's like you're talking sample rates of maybe 44 kilohertz or more.
Yeah, exactly.
So,
exactly.
yeah, I mean, compared to like 300 megahertz, that's nothing. You can just 300 or 40, what is that? Like 4 orders of magnitude slower. So you have plenty of time. So you could do stuff like that in software.
Okay, so you could probably pull off like an SD card and fill a buffer and just continue reading. So you could play a very long file and just bring it in.
Yeah, just bring it in piecewise as you need it. And then you kind of maybe have 2 buffers, right? Where you're streaming through one, and when you get halfway through or whenever, you tell it load the other buffer up so that it's ready by the time you get done with the current buffer, and then you have it load the next data into the other buffer.
Okay.
Yeah, we did this on P1, just all bit banged, and the DAC was just external, right? But we did the reading from an SD card and outputting PWM samples of 4-channel data to the 4 pins that would then be externally filtered and hooked up to an amp.
Yeah.
So it's still pretty trivial on the P2 though.
Yeah, it's even easier because the DAC's built in. We don't have any external requirements for the DAC now.
Yeah, and the DACs, the ADCs are not really good for hi-fi, but the DACs are okay. I mean, I have here, you know, since we went to these low dropout, super quiet regulators for 3.3 volts, and because the first run we had a switcher on the first eval board, you could hear the whine, but now we have these quiet LDOs, and then I've done some audio experiments where I have, you know, we have this little AV board that has headphone and microphone into it. In fact, let's see, it's right, this little thing here, right? So I think this is headphone, this is microphone. Anyway, there's a little microphone amp on here, and I can listen to the DAC outputs on there. They sound really good. I mean, I can't, and there is a slight difference between the dither mode, or the noise dither, and the PWM dither. The PWM dither is a little bit better. And so the best audio recipe is use the full span 3.3 volt 124 ohm DAC with PWM oversampling using that smart pin mode. And you get really good audio out of there. And it's super low noise in the background. It's you know, for our ears purposes, I think it's like 16-bit quality. It works pretty well.
Okay, thank you.
Okay, Chip, on your audio processing, do you ever find yourself working in one cog? Say you got a beat going in one, and you're trying to match a sound up in another cog in step with the first one. Do you ever run into any synchronization issues there?
No, I haven't done any coding like that. I would probably just take the approach of just having an agreed upon like marker using the main counter in the chip, and you know, having some agreement between cogs that, okay, this is our first time mark, and then we're going to add this many clocks every time thereafter, and then use that as a synchronization basis rather than try to signal between cogs or use IO pins. It works really nicely just to use the clock. If you have a deterministic time-based thing, just use the CT, you know, the 64-bit counter, and just use the bottom 32 bits of it, and just have an agreed base and an agreed offset thereafter. That, you know, there's no cumulative error. Everybody will be locked in at the same clock. And so for whatever the contract is, if someone has to have something ready, he gets it ready, the next guy picks it up. And you could arrange everything like that. That's how I would do it at first pass.
Thank you. I'm still trying to figure out how to get a second cog to bring up the sine wave in phase with the first.
Okay, so yeah, there's There's no one answer to that. There's a lot of ways you could do that. But okay, for something like that, is the frequency of your sine waves like 60 hertz?
Exactly.
Okay, so that is so low frequency that I wouldn't even worry about timing. You know, the way we have the hardware set up, it's for the super, super high bandwidth stuff that we have streamers and DAC channels and all this, and that's necessarily low res, right? But as you go further down the line, down to 60 hertz, well, you can just do that in software. So I would just maintain the phase in a global variable, right? That more than one cog can look at. So the master just is always updating that phase, and then everybody else picks up that phase and outputs based on that phase. Because, for 60 hertz, you can have thousands of samples within there within 60th of a second that everybody can be responsive to. It's slow enough that you could just do it like that. Just have someone calculate the master phase and everybody use the phase. But you were probably were you using the streamer to generate the sine wave?
Yes, it was some code that you wrote, and I just launched it into 2 separate cogs.
Okay.
The only way I've been able to sync them is by putting a delay between the 2 cogs.
Yeah, that's kind of variable, and you don't know for sure, right?
Well, it's repeatable. I can duplicate it, no problem. Once I find the magic number, it seems to work fine.
Okay, the way to do that would be to have some kind of time marker, because you know how many cogs you're going to be launching, right?